Afternoon, so you're welcome to attend any or parts of this. We'll have two sort of brief 20-minute, 20-plus questions presentations starting at 2, and then we have a shorter exercise session. We have to work twice as hard because at 4:30 we all want to learn about calculus of variation, and Professor Rabinowitz will give the colloquium over there. Okay, so I'd like to now talk about a special case of the sparse resultant, which is the unmixed sparse resultant. And by unmixed, I mean that our polynomials, our n+1 polynomials in star, all have the same support. Okay, I'm going to call that A. So in the notation from half an hour ago, A0 equals A1 equals A2 equals AN, and I'm going to call that simply A. I'm going to drop the subscript. So I have n+1 polynomials and n variables. They're all sparse, but they have the same support. And I'm going to write M for the number of monomials, and Q for the polytope. Okay, so Q is the common Newton polytope of n+1 Laurent polynomials in n variables. Now, since they all have the same support, it's convenient to write the coefficients of our system as a matrix, as an n+1 times M matrix. We'll call that matrix C. That's the coefficient matrix, right? So the n+1 polynomials, they all use the same M monomials. So the rows of my matrix are indexed by the polynomials. The columns are indexed by the monomials. So the first polynomial, I write the coefficients in the first row. The second polynomial, I write it into the second row, and so on. It's a rectangular matrix with n+1 rows and m columns, and I'll call that matrix C. So here's a fact. The resultant is a polynomial in the maximal minors of C. Okay. So by the maximal minors, I mean the n+1. So here, let's assume that M is greater or equal to n+1. There are more monomials than polynomials, okay? So then the maximal minors are the n+1 times n+1 subdeterminants, of which there are binomial coefficient many. M choose n+1. So I look at all the maximal minors, and I claim I can write this result, in this case, in terms of these maximal minors. Okay? Now this fact has to do with the invariance of these polynomials. Let me give you a keyword called invariant theory. So in the last week of June, I was just asked to make titles, for my lectures. So in the last week of June, we'll have a lecture on invariant theory. And this is a very, very, very special case of what's sometimes called the first fundamental theorem of invariant theory. So what's the point? The point is that our resultant, which is a polynomial function in C, it's invariant under multiplying C on the left by an invertible matrix. Right? So I have my coefficient matrix, and if I replace my polynomials by linear combinations of these polynomials, well, if they were solvable before, they're solvable afterwards, right? So if f, g, and h have a solution, then f minus 2g plus 7h and 11f, and some linear combination will also have a solution. Right? So the solvability of my system will be invariant under multiplying my rectangular coefficient matrix on the left by an invertible matrix. And it's one of those facts. So the fact is, if you have a polynomial function on the entries of a rectangular matrix that's invariant under left multiplication by a square matrix, then you can always express it in terms of the maximal minors. And we'll get to that in the end of June. In particular, it's true here. Okay? Now, also we can express the degree. Well, the degree, of course, is the mixed volume of, it's n plus 1 times the mixed volume of Q, 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 right? And that number is sometimes called the normalized volume. I'm going to use capital Q, capital V for the normalized volume. This is the normalized volume. So the normalized volume is simply n plus 1 times the usual volume. That's the normal. I'm sorry, it's n plus 1 factorial. So this is an integer. It's an integer. Okay, I'm sorry. So the normalized volume is, so I'm taking the volume and I'm multiplying, let's get this right, by n factorial. Okay? So that means that every lattice polytope has integer volume. It's the smallest, volume that has this property. Okay? So that's a fact. So let's see how we can understand this. So I would like to give you a geometric explanation and one example. Is the statement clear? So I'm claiming if you have an unmixed system, there is a sparse resultant, and we assume this polynomial is this Q is full dimensional, so it's essential. Right? So dimension of Q is n, so everything is essential, and then we can write it in terms of the maximum minors. So here's a geometric explanation. Now this explanation is again incomprehensible if you've never seen this kind of thing before. But as I said, if you're not here right now, please come next week. It'll be easier next week. Okay? So I'm just going to throw this at you. Okay? So the geometric explanation is the following. This unmixed resultant is a special case of what's called a Chow form. Yes? Okay, essential was the following. So I have a red polytope, a yellow polytope, a blue polytope, and so on. And they should have enough dimension. And enough dimension means I take any subset of these colorful polytopes. Let's say I take a subset of size 4. I add up 4 of these colored polytopes, then the Minkowski sum should be dimension at least 4.
Yeah, but then it depends on where you see those polytopes.
No. So they're given. I mean, I'm given.
In this case,
and here they're all the same.
So in that case, if you add, it doesn't change.
It doesn't change. So that's why in this case, essential just means full dimension. So
okay. That's
I have, I have the same polytope, and that polytope, all it means it's full dimension.
Yeah. So like you said, the essentiality is if you add 3 polytopes.
It has dimension at least 3. But here we're in dimension n. So I take any proper subset of my polytopes. So I have n plus 1 polytopes in n dimensions. I take any subset of size at most n of them, and I add them up, and I want to have, the dimension should be the number I add up, at least.
Yeah,
but if they're all full dimensional, I'm always going to get dimension n. So it's a non-issue here.
So bounded by the dimension.
The dimension is bounded below by the cardinality of the subset I take.
Yeah, but then the polytope is already 4 dimensional.
In this, exactly, it's a non-issue. So here, all we need is full dimensional.
So you're not using the definition of essentiality.
I'm not using it. So I used the definition of essential earlier when I had different Newton polytopes. I had a red line segment, a blue line segment, and a yellow triangle. They were different, and then I have to be a little bit careful. I have to think about essential. In the rest today, it's a non-issue. Yes?
Could you have zeros in your support as long as you multiply it by a matrix on the left so that the zeros become non-zero?
You mean in the entry C? Well, you mean whether I allow zeros in the matrix? Well, for me, C is a matrix of unknowns. Every coefficient is a distinct unknown. Okay, so C is a matrix, and it's filled with unknowns. Cij, the distinct indeterminates. These are no zeros. The matrix is full. The matrix is filled up with n plus 1 times m distinct indeterminates. Okay, so this sparse resultant is a so-called Chow form. It's getting worse, guys, okay, of the so-called toric variety. Okay? And the toric variety lives in projective space of dimension m minus 1. Okay? Let me unravel these words, okay? So in this department, there are many people who study toric topology. So that's a study of toric objects from the point of view of manifolds and topology. In algebraic geometry, we want our objects to be defined by polynomials, and we allow them to have singularities. In fact, that's important. So, you know, algebraic geometry without singularities would be boring. Right? I mean, it's easier to prove theorems. Professor Kwak has some beautiful theorems about varieties when they're smooth, but when they're not smooth, you know, it's just much harder and more interesting. So singularities are essential in algebraic geometry. So by toric variety, I really mean toric variety, not manifold. And for me, a toric variety is an object parametrized by monomials. Okay, it's a variety parametrized by monomials. Which monomials? Well, the A monomials. So this is parametrized by the monomials, or Laurent monomials, in A. Okay, you look puzzled. What's A? A is a set of m lattice points at n-dimensional space. But a lattice point is a monomial, right? It's a Laurent monomial. So A is a set of m Laurent monomials in n unknowns. That defines me a map from n space to m space, and I can organize it in such a way that the image becomes a projective variety, and that's the variety. Let's do an example. Let's look at this in an example. So here's my example. So in this example, n is 1 and m is 4. So Q is a one-dimensional polytope. So my one-dimensional polytope is a line segment of length 3. Okay? And it has m equals 4 lattice points. Okay? So F0 and F1 are univariate cubics. Okay? So this picture, this is, 0, 1, 2, 3. That's the support, right? So I have two polynomials in one variable x of degree 3. Coefficient plus coefficient x plus coefficient x squared plus coefficient x cubed. That's F0. And another F1. Okay? So I'm going to write these coefficients into a coefficient matrix. That's an n plus 1 times m matrix. That is a 2 by 4 matrix whose entries are 8 indeterminates. So C00, C01, C02, and C03. C10, C11, C12, C13. That's my coefficient matrix C. Okay? Now what's the toric variety? So the toric variety is the variety parametrized by the monomials in A. Well, what are the monomials in A? The monomials are 1, x, x squared, and x cubed. Right? So look at all the points of the form x, 1, x, x squared, x cubed, where x is a complex number, maybe close it up, and that's a curve in three-dimensional space. That's my toric variety. This curve is also called the twisted cubic curve. So here's the curve. So it looks like this. Okay? It's a curve in three-dimensional space, parametrized by the monomials in A. A is a set of 4 monomials in one variable, namely the monomials x to the 0, x to the 1, x to the 2, and x cubed. Okay? Now what is the resultant? Well, it describes the solvable systems, right? So it describes all matrices such that the corresponding system of 2 equations in one variable have a common solution, right? So it describes the set of solvable systems star, right? So geometrically, what does it say? Well, that says I'm interested in all matrices such that the kernel meets the toric variety, meets the curve. In P3, right? So that's by definition, right? So my system has a solution. Well, that means in the kernel of the matrix, there's going to be a vector of the form 1, x, x squared, x cubed, for some x. Right? Is this clear? Right? So I have 2 equations in one variable of degree 3. I'm writing the coefficients like this. Right? There's a common solution x if and only if there's a vector of the form 1, x, x squared, x cubed in the kernel. Or equivalently, the kernel meets the curve. Now geometrically, what's the kernel? Well, the kernel is a line in P3, right? So this kernel, well, it's a 2x4 matrix with unknown entries, let's say, The kernel of a 2x4 matrix is a 2-dimensional linear subspace in the 4-dimensional vector space, but in projective space, that becomes a line. Okay, so what's the upshot? I'm interested in the set of all yellow lines that meet the red curve. That's the resultant, right? The resultant is the set of all, or z bar, the variety cut out by the resultant, is the set of all lines, right? So the lines, of course, given by these matrices, so I'm interested in these lines. Now, who's Chow? Chow was a Chinese mathematician who studied with van der Waarden in Hamburg. S.S. Chern, as you know, a very distinguished Chinese differential geometer, studied in Hamburg. So did Chow in the 1920s. And he developed the Chow form in general in a joint paper with van der Waarden, but really it goes back to Cayley. So Cayley was the first to do this in 3-dimensional space, and Chow did it in general in arbitrary dimensions. And Cayley asked the following question. Okay, so let's get ourselves into the mindset of Arthur Cayley. Okay? It's 1840, maybe 1845. Cayley was a lawyer in Ireland, and he liked math. He wrote hundreds of papers about math, each and every one worth reading. I urge you to read Cayley papers. A Cayley paper a day keeps the doctor away. They're short, always to the point. And he asked the following question. Okay? Cayley said, well, a plane curve has a good representation. It's given by a single equation. That's good, right? A surface in 3 space has a good representation. It's given by a single equation. That's nice. What about a space curve? How come we don't have a good representation for a space curve, right? Well, if you have a space curve, well, you could certainly oftentimes write it as the intersection of 2 surfaces, right? You can write it sometimes, not always, as by 2 polynomials, but they're not unique, right? There's no canonical representation. So Cayley said, wouldn't it be nice if we could write down a space curve by a single polynomial? He said, I show you how to do it, right? So let's take a space curve, right? So here's how you can get a single polynomial. Let's say, let's look at the set of all yellow lines that meet the red curve. Well, that's codimension 1 condition in the 4-dimensional space, in the 4-dimensional Grassmannian of all yellow lines, right? So I have a 4-dimensional space called the Grassmannian of all yellow lines. Inside that Grassmannian, I have a codimension 1 condition on the yellow lines that meet the curve. Just write that equation. That equation describes the curve. Okay? That was Cayley's idea in 1845. And that works for any projective variety, and that's the result of van der Waarden and Chow from the 1920s. So let's do it for the twisted cubic curve. So for the twisted cubic curve, and that's the result. Okay? So this is the Chow form, Chow-Cayley form. So in this case, the way I like to write the resultant is that the determinant of a matrix 0, 1, 0, 2, 0, 3, these are brackets, 0, 2, 0, 3 plus 0, 1, 2, 0, 1, 3, 0, 3, 1, 3, 2, 3. Okay, so this is the result. This is the Bézout resultant. We saw it last week. Everybody other than Matt saw it last week, right? So this is the Bézout resultant for 2 univariate cubics, Bézout matrix. Okay, so I promised this fact that the resultant is always a polynomial of degree the volume in the brackets. Well, what's the volume, the normalized volume of this 1-dimensional polytope, right? This 1-dimensional polytope is a line segment of length 3. So the volume of this 1-dimensional polytope is 3, right? So according to this fact, the resultant is a polynomial of degree 3 in the maximal minors, and that's what it is. So these brackets, they stand for the maximal minors. So bracket ij stands for C0i times C1j minus C0j, 1i. Okay, that's it. That's the formula, right? So that is the condition. That's the univariate resultant, the one we saw last week. It's the condition for 2 polynomials of degree 3 in one variable to have a common root. Or equivalently, the Chow form of the red twisted cubic curve. Okay, so that's the Bézout matrix. Okay, I mean, much more could be said. Now, of course, so a Bézout matrix is a matrix that has this particular form. This works in general. These maximal minors, they satisfy the Plücke relation. So 0, 1 times 2, 3 minus 0, 2, 1, 3 plus 0, 3, 1, 2 is equal to 0. Those are the algebraic relations. That's a unique algebraic relation among the 2x2 minors of a 2x4 matrix. These guys are nodding because they did the homework. The homework asks for the algebraic relations among the 2x2 minors of a 2x5 matrix. And one of you will present that at 3 o'clock sharp today, right? That's a special case of that, okay? So Bézout matrix is a matrix like this that satisfies this relation. The inverse of a Bézout matrix is a Hankel matrix, a non-trivial theorem. So the inverses of Bézout matrices are exactly Hankel matrices. Well, a Hankel matrix is almost the same as a Toeplitz matrix. So if we reorganize things a little bit by this permutation matrix, then the inverse is a Toeplitz matrix. Today at 1425, we'll hear a discussion on Toeplitz matrices. So I claim the inverse of such a shifted Bézout matrix, provided it satisfies the Plücke relations, the one from the homework. Those are exactly the inverse Toeplitz matrices. So we'll hear about this afternoon. Okay, so I have two more comments. Any questions? Is this clear? So what's the Chow form and why is it the resultant? So this works in general.
How does it extend in general then? Like, if you have something and more than just one variable, you know, we just have this univariate system. So
how do we find the formula?
Yeah.
Okay, that's an art. Okay, so in general there is always the resultant. So this is the Chow form of toric variety, is always a polynomial in brackets of the yellow degree. But finding good formulas, that requires practice. But the good news is you will practice this afternoon. So, you know. Okay. So 2 comments. Let me wrap up with 2 comments. So let's do that here. So there's one more section which I will not go over, but I'll just tell you what's in it, you know. So this is the resultant of 4 trilinear equations. And that was a challenge. So somebody was very interested in this, and we worked it out in the book. So a trilinear equation is exactly what you think it is, right? It's an equation in 3 variables x, y, and z. That's linear in each x, y, and z. So it has 8 terms, right? So in this case, n is 3, m is 8. The corresponding polytope is a 3-dimensional convex polytope with 8 vertices, known as the 3-dimensional cube. And there's a formula. Okay. Now, I'm mentioning this because in the exercise this afternoon we'll do the smaller case. We'll discuss the case of 3 bilinear equations where the polytope is the 2-dimensional cube, also known as the square. So we'll discuss that this afternoon. Now this is a nice example. So the formula you find in the book is wrong. There's a typo. So there's a long. So if anybody have the book or the device, you guys have a device. So there's a formula. Okay, on page 56. So you're encouraged to get your Samsung device out and look on page 56. There's a formula here. It's a determinant, you know, page 56 at the bottom. It's a certain 6 by 6 matrix in brackets, and there's a typo somewhere. And how do you find that, right? So the book was published, you know, there was a typo. And this was found, we had a collaboration on a paper called Algebraic Factor Analysis with Matthias de Ton, then at the statistics department in Chicago. And we actually needed this formula for a statistics project. I said, hey, I have a book, it's in there, and then it was wrong. It gave wrong answers, and so we fixed it. So it's actually fixed in this paper. So there's a book called Algebraic Factor Analysis. So factor analysis is a term from psychometrics. So it's something that people in psychology who use statistical models, they do factor analysis, and anyway, we fixed the formula. But this afternoon, we will not be worried about the 3-dimensional cube. That's a polytope that's way too high-dimensional, but we're going to try the 2-dimensional cube. So I agree with you, Matt, the 1-dimensional polytopes, they're a little bit too easy, you know. 3-dimensional polytopes are a little bit too hard, but 2-dimensional polytopes are just right. Okay. Now the second remark is there's a nice example where this gets used for an optimization problem on page 53. So on 53 is sort of another example of one of these resultants, and it gets used to sort of solve a certain optimization problem exactly. So that's all I had to say about elimination, and that leaves us with 25 minutes this morning for the next topic. Any questions about elimination? Everything clear? Here are the exercises. So this is for this afternoon. So exercises number 2. Please, if you did not take it last time, take one. And these are the ones for tomorrow. We will meet tomorrow, no temple. Tomorrow we will meet and we'll work on exercises number 3 tomorrow. Okay, so this afternoon we will do exercises number 2. We will do exercises in elimination. Tomorrow afternoon, we're running out of time, guys. You know, in 2 weeks there's a national holiday and so on. We got to get some work in now. Okay, so tomorrow we will deal with decomposing varieties. That's our next topic. Okay, so today after the colloquium and before tomorrow at 10 o'clock, I'd like you to take a look at exercises number 3, which are over there, and try to solve at least one. If you are like me, then you can look at that at 5 a.m. tomorrow morning, but I'm an exception. Most students sleep in the morning. They like to stay up at night, so tonight you can look at exercises number 3. Okay. So the next topic is decomposing varieties. So in the book, there's a section 5.1 starting on page 59. What does it really mean to solve a system of polynomial equations? Well, first of all, what's a polynomial system? A polynomial system is an ideal. So I is an ideal in a polynomial ring. Solving the system means something. Okay? Now there are very, very different things what that might mean. Okay? So for many practitioners, it means finding one solution point. And finding one solution point means that each coordinate, which is a complex number, an algebraic number, and you want to give a floating point approximation for the real part up to 8 digits, and a floating point approximation for the imaginary part up to 8 digits. That's what some people mean. Other people mean different things. Maybe finding all real solutions, finding all complex solutions numerically, finding all solutions symbolically, but maybe typically the solution set is infinite. Right? There will be a curve, right? There's a dimension, right? The dimension of the variety is the largest cardinality of a subset of the variables, such that every monomial in those variables is standard. That number might be 3, right? So there's a 3-dimensional variety, so you can't list all the solutions. You have to describe the variety somehow. So in my opinion, this is my opinion, okay, you can disagree with this opinion. So my opinion, solving means finding an irreducible decomposition, describing typically the irreducible decomposition of the variety. So the variety of I has a finite decomposition into varieties given by some other ideals, P1 up to PR in C to the n. And each of these pieces is irreducible in the sense that it's not the union, the non-trivial union of two other varieties. So variety is irreducible if it's not the union of two varieties that are proper subsets, right? So, and we can always find such a thing in a Noetherian ring. Okay? So what I'd like to do now, in the last 18 minutes, start setting up some language to speak about this decomposition. This requires a little bit of language of algebra. So here each Pi is a prime ideal. Okay? I'm going to give you a definition in a moment. So prime ideal is like prime rib or prime time. It's a very good ideal. Okay? Prime ideal is like prime ideal. It's a wonderful ideal. Okay? That's one definition. When I speak to biologists, by a prime ideal, it's simply the ideal of, it's the set of algebraic relation among a bunch of polynomials. Among friends, it's a pretty good definition of prime ideal. But since we're here actually learning the language of nonlinear algebra, let me give you an actual definition. The actual definition goes like this. For every polynomial, that's the polynomial ring. If I take P colon F, remember the colon ideal, I get P back. Okay, that's the definition of prime ideal, right? So if P is an ideal, then P colon F is another ideal that contains P. It's the set of all polynomials that multiply F into P, right? It's a one line, it's a built-in command in Macaulay, singular, so on. And if you don't get anything new for any F, then we call that a prime ideal. Okay, maybe we want minus P, huh? F naught in P. Okay, so F naught in P. Okay, so for everything that's not in P, you know, you don't get anything new. Okay? Now, here's another thing. Maximal ideals are prime. So sometimes, you know, you learn. So maximal ideal is a proper ideal. It's an ideal, but it's maximal with respect to inclusions. They are always prime. That's immediate from this definition. If you think this through, this immediately implies that the maximal ideals are prime. Okay? Now, when I was a student, so people always, old people like me always talk about the olden days, right? In the olden days, right, the snow was whiter and the grass was greener and we had nothing to eat and we hiked 15 miles to school. And okay, so when I was your age, I was a student, like some of you, at a technology institute. So KAIST is an engineering school, but you are very, very, very lucky because at your engineering school you have algebra and combinatorics and a wide spectrum of mathematics, topology, toric topology, whatever, right? The engineering school I attended, the only thing that was offered was numerical solution to partial differential equations. Okay? There was one course called Algebra that sort of did a little bit of algebra, and I remember this was very memorable, and we learned about rings. And there were two rings. There was the ring of integers, and there was polynomials in one variable. And that was the only rings at Technische Hochschule Darmstadt when I was a student. And we learned that every prime ideal is maximal in my engineering school, right? Because in those two rings, every prime ideal is maximal. But you guys know that there are many, many, many more prime ideals than maximal ideals, right? Because there are many, many more rings. Okay, so these are prime ideals. Now, how to decide whether a given ideal is prime? How to decide? It's a true story, Daniel. Whether a given ideal is prime. Okay? So I give you, 10 polynomials and 4 variables and generate an ideal, right? So question, yes, no question, is this a prime ideal? Okay? Well, not easy is the answer. Okay? The definition of prime ideal is very easy, but checking whether a given ideal is prime is not easy. There's a built-in command in Macaulay 2 called isPrime, which comes back with either true or false or doesn't terminate, usually the last. Okay? So it's not an easy thing to check whether a given ideal is prime. Okay? But sometimes, here are some examples. So for example, in one variable, x squared minus cube is a prime ideal in a polynomial ring in one variable. But if we make the field a little larger, it's not a prime ideal. Right? So if we replace the field of rational numbers with the field of real numbers, this is not a prime ideal. This ideal I is not prime, because if we take f to be x plus the square root of 3, then that f is a witness for non-primality. Okay? So it depends on the coefficient field. Okay, so now let's develop a little bit of language to speak about this decomposition. So prime P, or prime ideal P, is associated to the given I if some condition holds. So we're given our system of equations, we want to break it into pieces, right? So maybe there's a surface and a curve and another surface, sort of break the variety into pieces. So a prime is associated to I if there exists a polynomial such that I colon f is P. Right? That's it, right? If there's a witness, so I'm going to call that a witness. So given an ideal, typically not prime, I, and some prime ideal P that wants to be associated to I, well, it is in fact associated precisely if there's a polynomial f, a witness f, such that I colon f is P. Okay, that's the definition of associated. We write as of I for the set of all prime ideals that are associated. So prime and associated to I. Okay? It's the set of all prime ideals in the polynomial ring that are associated to the fixed I. So I is given. I is given a system of polynomial equations. I is the set of all prime ideals that satisfy this condition. Each and every one of them has a witness. Okay? Those are the associated primes. Now, here's a little proposition. So we'll practice this tomorrow. Okay? So tomorrow afternoon with exercises 3, we'll practice associated primes and things like that. Okay? That's the exercises 3. Was a handout. Proposition 5.1. For any ideal in a polynomial ring, the set of associated primes is a non-empty set and finite. Okay? It's a non-empty finite set. So a given ideal I has at least one associated prime, and the total number of associated primes is a finite number. Okay, that's good. So we have a computational question. Given I, find the associated primes. Okay? Let's do an example. Let's do an example in one variable. Okay? Suppose we're in one variable and my ideal is x to the fourth minus x squared. So in one variable, every ideal is a principal ideal because the polynomial ring is a principal ideal domain. And in my technical school, all rings were principal ideal domains, and therefore all prime ideals were maximal. Okay? So in the polynomial ring, in one variable, x to the fourth minus x squared generates some ideal. So I claim this ideal has three associated prime ideals. Okay? So the prime ideals are that are associated x minus 1, x plus 1, and x. Okay, so these are prime ideals because they're maximal, right? So they are prime, and I claim they're associated. You can find a witness in each case that witnesses this prime. So they are the maximal corresponding to the three roots, 1, minus 1, and 0 of this ideal. Okay, so whenever you tell me the list of associated primes, I'm going to ask you for a witness. Give me a witness. Okay, so what's the witness? So for example here, the witness could be x cubed plus x squared. So if you take this f, then I colon f will be this p. That's a witness. But this is actually associated. This one, for example, x cubed minus x squared will be witness for that. And x cubed minus x will be witness for that. Okay, that's it. There are three associated primes, and I've given you witness. So this was easy. In one variable, it's fairly easy. But in several variables, it's not so easy. Okay? So here is an example in 4 variables. Looks very, very simple. Okay, so let's take the variables to be a, b, c, d. So let's take AD plus BC, AC, and BD. Okay? So these are my equations in a polynomial ring in 4 variables. Okay? So you can ask questions like, is this a prime ideal? And so on. Well, turns out that this ideal has also 3 associated primes. Okay. So the first one is AB, second one is CD, and the third one is ABCD. Okay? 3 associated primes to this ideal. Maybe you don't believe me. Well, I can give you a witness. Okay? So for each of these prime ideals, I'm going to give you a witness. I have to find an F such that I colon F gives these prime ideals. So, and we're going to do this live now. We have 6 minutes. We have an expert in commutative algebra back there. You keep us honest. Okay? Anybody know a witness for AB? Audience participation. So I always tell my calculus students, if you don't have questions for me, I have questions for you. I never ever ask people in the first row. I always ask people in the last row. Feng, do you know a witness for the first prime? You know a witness? So we're looking for an F such that I colon F is AB. So F should be a polynomial that's not an I. But if I multiply it by A, it lands an I. Then if I multiply it by B, it also lands an I. Anybody have a suggestion?
D plus C.
C plus D. This one. Okay, well, if we multiply this by A, for example, we get AC plus AD. Right? AC is in the ideal, but I claim that AD is not in the ideal. Okay? Well, that requires an argument. Well, how can I convince you that AD is not in the ideal? Well, I calculate, how do I convince you that anything is not an ideal? I calculate a Grobner basis. I do the normal form of AD against the Grobner basis, and it's not in the ideal. Okay? So, sorry, I know this does not work, but almost. You're close.
How about C times D?
So the last row, that's where the winners sit. Okay, let's try C times D. Okay, so we multiply, so it's not in the ideal. Okay, well, if we multiply it by A, it's in the ideal. We multiply it by B, it's in the ideal, and it's actually a witness. Okay, so if you go on your device, I call it too, you say on future generation of Samsung, so I:CD, you know, AB, Siri, tell me, you know. How. Okay, then by symmetry, you know, we get AB. And finally the last one, so this is the unique homogeneous maximal ideal. I claim that's also associated. Can we find something there? So I'm looking for a polynomial. It's not in here. But if I multiply it by any of the variables, I get in there. So AD? Let's try AD. So AD times D, let's do times A. AD times A, that's congruent to ABC, and that's in the ideal. Times B, it's in the ideal. Times C, it's in the ideal. Times D, it's in the ideal by this relation. So hooray, we win. Okay? Okay, so why don't we leave it at this? Okay, so let's take a break of 2 hours and 3 minutes, after which Wang-Rui Li, straight from Pohang, will tell us about ED for Fermat, and then the rest of the program will unfold. Please take exercise sheets number 2 and number 3.